Hello? Hello? Can you see the board?
Yes, sir.
Yes,
Yes, yes, sir.
yes,
Okay. Just continue what we were doing last time. Also introduce what is the theta notation. Okay. All the other functions and all remain the same. They are from positive integers. Integers. The functions and all are from positive integers to positive integers. All of that remains the same. Now say f of n is theta of g of n if both the other conditions hold true. We go g of n and then must be omega g of n. Okay. What does that mean? That there exists. So for big O and big omega, there will be two constants, and then there is n naught beyond which eventually one of them is true, the other is true. So you'll have n naught n1, but then you can take n naught to be, you can take it to be the largest one among the two, right? So convince yourself when I write it this way: C1, C2 greater than 0, and n naught positive integer. That what does the first one say? F of n is less than or equal to C1 times n. Second one says f of n is greater than or equal to C2 times. Okay. The n naught I have taken to be common because for each you will get a different n naught, and I can take the maximum of those so that this holds true. So I'm taking the same n naught for both. Correct? Now immediately you can see, so mark, you don't need to go into the C1, C2 business just by looking at the definition. So check this. F of n is theta g of n if and only if g of n is theta f. This much is definitely true, right? So now there is also another version. So let me also write it here in the title: theta notation and tilde notation. So what's the tilde notation? I'll write it here itself. It's simpler. So for each one, you had a stronger version, right? For big O, you had a stronger version in terms of limits. For big omega, you had a stronger version in terms of limits. For theta also, there is a stronger version in terms of limits. Okay? So we say f of n is tilde g of n if limit n tending to infinity, f of n by g of n is equal to 1. Just 1. Okay? They grow at exactly the same rate. That is the idea. Just 1. Right? So let's look at some examples. Let me just show you one simple example that clarifies these things. So examples. So you can always say that take n square. N square is theta n square plus, in fact, a times n square plus bn plus c for fixed a, b, c greater than 1, greater than or equal to 1. Greater than 0, but we'll stick to 1. Okay. You see why? You just have to show that they are big O and big omega of each other. So, first part. So we have an square plus bn plus c. So I have to bound it below less than or equal to an square plus bn is less than or equal to n square, and c is also less. C times 1 is also less than or equal to n square. So cn square. Okay. So a plus b plus c is your constant for all n greater than or equal to. A plus b plus c is your constant because a, b, c are fixed here. Okay. Let me write it again. Constants. Fixed means constants. Right. So this means, okay, the way we have written, this means n square is greater than or equal to 1 upon, I mean, you can write it either way, but I'll write it as which means n square is big omega. Okay. So you have bounded an square plus bn plus c in terms of n square. Now, how do you bound n square in terms of an square plus bn plus c? So that's where the constants help a little bit. I've taken a plus a, b, and c to be greater than or equal to 1. So already we will have n square less than or equal to an square because a is greater than or equal to 1, and that is less than an square plus bn plus c for all n greater than or equal. So the constant here is just 1. So this implies n square is big O. Okay. So you have big omega and big O, and therefore it is theta. Now the constant need not always be greater than or equal to 1. They could be positive, that is enough, but then you will just have to adjust this so that this term becomes greater than or equal to 1. So you'll have to multiply a with something more so that the constant here becomes greater than or equal to 1. That's all. No other change. Okay. So let's continue. So yeah. Okay. So let me write down that as the second thing. N square is theta an square plus bn plus c for fixed a, b, c greater than 0. Let me give this to you as an exercise. Okay. There is only, so one way is anyways clear. The big omega part does not really change. Only the big O part you have to just be a little bit more careful. So think about it. Okay. Great. Now let's also do something. Let me show you that n square is in fact tilde an square plus bn plus c if and only if a is equal to 1, not otherwise. Okay. So what are we supposed to look at? We are supposed to look at the limit of n square by this. but we can also look at the limit of the other one. So going to previous slide, if you look at this limit is supposed to be equal to 1, right? So the reciprocal limit will also be equal to 1. So let me write it as a note here itself. Remark f of n is tilde g of n if and only if g of n is tilde f of n. Okay. Why is this important? It is important because sometimes you can look at the fraction and decide which way you want to take the limit. It might be easier to solve the limit by taking g of n by f of n instead of taking f of n by g of n, that kind of thing. So you can check. It does not matter which way you do. As long as the limit stays 1, the tilde thing is true. Tilde condition is true. Doesn't matter how you take it. So in this case, instead of taking the limit n square by an square plus bn plus c, it is easier to take an square plus bn plus c divided by n square. Much easier, right? So what happens here? We have limit n tending to infinity, an square plus bn plus c divided by n square. So I'm assuming a, b, c are greater than 0, okay, before solving the limit. What is this equal to? This is limit n tending to infinity, an square by n square is a plus b by n plus c by n square. B by n and c by n square will go to 0. This limit is equal to a, right? Thus, we have this. So we have click. See why? Because it is tilde if and only if this limit is 1, if and only if a is equal to 1. All right. So those are some simple examples. We can also show something like not tilde. That is much easier. So since it involves limits, it's much easier to check. So few examples we have already seen. So now we know that square root n is not theta n, and something like n is not theta n square, because one of the two, big O, big omega, one of the two is not correct, is not true. We have seen that before. Okay. Therefore, even if one of them is not true, it cannot be theta. All right. Similar thing holds, in fact, even for tilde. So square root n is not tilde n. N is not tilde n square. So both of these just check. I mean, the first one is easy to check. You have already proved it in the previous slides. This one, check by looking at the limits. In fact, you can already see that the limit either goes to infinity or 0 depending on how you take it. Okay, so it's not tilde. All right, so that was it. Now we have some very simple properties. So one is, if f of n is little o g of n, then it implies f of n is big O g of n. You see why? So let's prove this quickly. Very simple again. So when f of n is little o g of n, by definition, It means limit n tending to infinity, f of n by g of n is equal to 0. Right? F is much smaller than g. That is the meaning. Now just use the definition of limit. Okay. So this implies, by definition of limit, for every epsilon greater than 0, there is an n naught such that fn by gn is less than epsilon. Now it should be mod fn by gn, but f and g are positive. Okay, so I can ignore the mod. I'll leave it here, but you don't really need to write the mod for all n greater than or equal to n naught. So now let me pick there is some n1. Let me fix epsilon to be 1. There is some n1 such that fn by gn less than 1 for all n greater than or equal to n1. What does that say? Fn is less than or equal to, less than means less than or equal to gn, right? This by definition says Fn is big O gn. Okay. Very simple. The limit definition is much stronger than the constant definition. That is the idea. Okay, much stronger. All right. Let me quickly mention a remark. Converse is not true. Okay, check. In fact, one of the examples we have already seen is a counter example. Okay, so check in the sense find a counter example. Okay. So what does it mean? You have to find a function f and a function g such that fn is big O gn, but fn is not little o gn. All right, we have already seen such examples. Right, just go back to the previous slides later and find a suitable counterexample. So converse is not true. All right, so analogous statement. Now the reverse. So if fn is little omega gn, then it implies fn is big omega gn. Okay, so this is exercise. Try using the definition and limits. Okay, but let me give you a shorter proof using all that we have seen so far. Shorter proof is fn is little omega gn. This is if and only if gn is little o fn, right? Because it's the limit, you look at the reciprocal. We have already seen that. So this implies gn is little o fn. But then by previous property, by what we just saw, this implies gn is big O fn. But then this implies Fn is big omega Gn. Okay. So this if and only if thing between big omega, big O, little o, and little omega, check if it's not clear. Okay. Very, very easy to check. The definition just gets reversed. I think one of the two we have already done in the class, the other maybe we have not, but just go and check by definition. Two-line answer. Okay. Right? This is what it is. Once again, converse is not true. Again, example comes from what we have seen before. Okay. Find a counter example. Counter example is already there in what we have seen so far. Just look at it. Okay. Next one. Now, this is even easier. Okay. So this I want to leave it to you. So f of n, if it is tilde g of n, then it implies f of n is theta g of n. Okay. This should now be clear to you because of the limits and stuff that we have been seeing so far. It should be more or less clear how to get this, but let's write it down. So if fn is tilde gn, by definition, we are just saying the limit is 1. Can you hear me? Hello?
Yes.
Yeah. So fn is tilde gn implies the limit fn by gn is 1. Again, use the definition of limit. So this implies for every epsilon greater than 0, there is a not positive integer such that now you need to use mod. Right? So mod fn by gn minus 1 less than epsilon for all n greater than or equal to n naught. Write it down further. This implies okay, just check. Let me write it down directly. 1 minus epsilon gn less than fn less than 1 plus epsilon gn for all n greater than or equal to n. Okay, just check this. Right? This is how it will be. In fact, there is again mod, but these are positive functions. So I'm forgetting mod for the moment. So this means fn by gn is between 1 minus epsilon and 1 plus epsilon. And I have just multiplied gn on both sides. Okay. So let me fix. So I need constants on both sides, right? I want to prove theta. So I will take epsilon to be something less than 1. So let's say 1 by 2. There is an n1 positive such that 1 minus 1 by 2 is half. So half gn less than or equal to fn, less than I can replace by less than or equal to, and 1 plus epsilon is 3 half for all n greater than or equal to n1. But this is precisely when the definition of theta. Okay, we just saw. So this implies Fn is theta g. Okay. Again, remark converse is not true. Find a counterexample. Okay. Something even stronger is true when you consider limits. So you don't need the limit to be 1. The limit could be anything positive. So if lambda is a positive constant, lambda greater than 0, and limit n tending to infinity, Fn by Gn is lambda, then Fn is theta Gn. Okay. Now this I leave to you as an exercise. Exactly the same proof that we have done here. Instead of 1, you have to work with lambda. So you'll get lambda minus epsilon, lambda plus epsilon. You just have to choose epsilon so that lambda minus epsilon is positive, and then you'll get the same thing. Okay, same proof. Just try repeating it. This is exercise. And once again, the converse is not true. Find a counterexample. Okay. All right. So that is as far as I wanted to do today. Little theta, little tilde, sorry, little tilde, big theta, and this other limit. Yeah, this is enough. Now we just have to solve some more problems and exercises. Okay. So let me do one thing. So as I said last time, all the exercises that I'm mentioning in during the class, try writing it down. Okay, write it down and check that all these things are fine. Plus some problems from the book. So I'll do one thing from the book. The problems that I want you to solve, I'll write it down and post as a tutorial sheet, and then you can try solving them. Okay. So I think you have some sort of a vacation going on. So I won't give too much, but a little bit I will expect you to work even during the vacation.
Where are you going to post, sir? Where are you going to post in the data structure channel?
Yeah. Everything I'll post there only. When I post it, I'll put a message on WhatsApp. Okay? I will not post anything anywhere else. Don't worry. And we'll see. I might ask you to finish all of this and submit at some point of time. Okay. So up to when is your vacation? We need to look at the dates. So this is the end of today's class. I don't want to do too much. Okay. Just stop sharing. Yeah. So up to when is your vacation?
4th of September.
4th.